in 11.6. So that'll be more of our focus today, but there's a couple things I want to mention about the cross product. So first off, just to give you a conceptual idea of what's going on with the cross product, or why we need this other form of multiplication for vectors, torque is something that we can all relate to. It's the force acting on an object that causes it to rotate. And the object moves around an axis, okay? Think of a wrench, right? When you're trying to tighten a nut, that axis would be the nut, and you use torque to spin it. So basically, we can look at torque as a vector valued quantity. So what we can look at is the force and the distance vector. So the force would be the force being applied to the lever, and the distance is the distance from the axis of rotation that we're applying the force. It'll make a little bit more sense when I put a diagram up here. But torque depends on those two things, right? Again, this is something we can all relate to. The longer the wrench, the more torque you get. So we got our pivot point, and let's say we're applying a force F. Well, that force F is being applied some distance from the pivot. So that was the distance being referred to. Now, the only thing that's going to rotate this wrench or this lever is the force that's perpendicular to it. Any force that's parallel to it isn't going to move it. So we only care about the component of force that is perpendicular to the lever. So let's give some angle theta. Notice that that perpendicular side is the opposite side. So F perpendicular is basically the magnitude of F sine theta. This is basically our geometric definition of the cross product. So when we're measuring torque, it is the same idea. Two things going on with torque. It has a magnitude and it has a direction, because if we think of screwing in a bolt or a nut, that has a direction, right? It's going into an object. So let's talk about the geometric definition. Again, the idea of torque, just to give you some concept of what we're talking about with cross product. So if we have A and B are two vectors, then A cross B out of the dot. That's how we know which type of multiplication it is. The magnitude is magnitude of A, magnitude of B, sine of theta. Now, just like with the geometric definition of dot product, this is great if we know the angle between the two vectors, which is not always going to be the case. So we're going to like the algebraic definition better, even with cross product, just like with dot product. Now, this is a vector valued quantity, so it has both magnitude and direction. And the direction is going to be perpendicular to the two planes that the cross product lies in. In other words, for the cross product of A and B, they lie in this plane on the screen. A cross B is either going to be perpendicular out of the screen or perpendicular into the screen, depending on if we do A cross B or B cross A. We're guaranteed it's going to be perpendicular. The only question is it coming out of the screen or going into the screen? And one way of determining that is with the right-hand rule. Now, we only need the right-hand rule if we're using the geometric definition. When we use the algebraic definition, we're going to get a vector as our output. So the direction will be will be inherent in the vector. You don't have to calculate that separately. But the way the right-hand rule works, there's a couple different ways that this is described. But here's basically how the right-hand rule works. You put your forefinger in the direction of the first vector. You put your middle finger in the direction of the second vector. And whichever way your thumb is pointing is the way the cross product is going. So we'd be, if you can imagine A, B, then it's up, right? But if we were to reverse that, A, B, now it's down. or sorry, BA, right? BA now would be down. Another way of that the right-hand rule is sometimes described is you put your fingers in the direction of the first vector, curl them in the direction of the second vector, and whichever way your thumb ends up pointing is your direction of your vector. Because you can imagine A cross B goes this way, but B cross A goes that way. So both of those are fine. It's not going to be something you're going to use a whole lot in here because, again, we're going to use the algebraic definition more often. Specifically, let's get into the algebraic definition. You guys saw this in the video, so I'm not going to spend a ton of time on it. But it's a formula that looks like this. It's a crazy looking formula. For those of you guys who have or are taking linear algebra, this can be done as the determinant of a 3x3 matrix. I'm not going to go over that right now because not everybody needs to know that. Again, for the exam, remember, you're going to have your note cards. So this could be a formula you put on your note cards. I don't want to make memorizing how to do cross product a big part of this class. Knowing when to use cross product is going to be the big part of this class. Okay. So I'm not going to worry about the determinant of a 3x3 matrix, but for those of you guys who are doing linear algebra, that's all that's really being done. All right. Now I do want to point out, you know, what might look like a discrepancy initially between this formula up here and the formula down below, and that is on the middle term. Notice up here it's A3B1 minus A1B3, but down here it's A1B3 minus A3B1. Well, that's because of this negative in front here. That would reverse the order to make it look like this one up here if you distributed the negative. And for those of you guys who have taken a determinant of a 3x3 matrix, you know why that negative is there, because you switch signs every time. But I don't want to bog you down with the determinant of a 3x3 matrix if you're not currently in linear algebra. Again, we don't try to memorize that formula, just have it be one that, you know, is on your note card. All right, just a few applications that are kind of interesting. Area of a parallelogram. So if we're looking at A cross B, it turns out it'll find the area of this parallelogram. And the reason may not be obvious at first, but if we think of the height of that parallelogram, right, and that's the same as the h over here, well, that's the opposite side. So we know h equals b, the magnitude of b sine theta. Then we're at our geometric definition because we're going to multiply the base, which is the magnitude of A, times the height, which is the magnitude of B sine theta. There is the geometric definition of our cross product. So the magnitude of the cross product actually gives the area of the parallelogram formed by the two vectors. We don't need to derive that. It's just an interpretation, a geometric interpretation of the cross product. Now, what's really nice, what's nice and follows, I don't know where. All right. What follows from that very nicely is there's also a triangle formed by the two vectors, right? Well, notice that's exactly half of the parallelogram. So cutting that magnitude in half gives the area of the triangle formed by the two vectors. We can extend this a little further. And I think you guys saw this one in the video. If you did A dotted with B cross C, you get a triple scalar product because it ends on a dot product. And that scalar has a geometric meaning too. It's the volume of a parallel pipette, which is this guy here. Now, why this works? Well, actually, I'll show you on the next one. But we know B cross C gives the area of this parallelogram on bottom. Multiplying that by the height of this thing would give the three-dimensional volume. Well, that height is just the vector projection of A in the direction of B cross C. Because we know B cross C has to be perpendicular, just like the height has to be perpendicular to this box. So what we end up doing, we know B cross C gives that yellow area, right? And then A dotted with B cross C gives the vector projection, which is essentially the height. Therefore, that scalar that we get is the volume of this box. So pretty cool, but again, something we might do in a homework problem, but not not our ending point. The biggest thing about the cross product is that it gives us a vector that is parallel to the plane that the two vectors we're cross producting lies in. And we'll talk about in 11.6, one of the applications that'll make this, oh, that's why we do it right away. So just a little comparison of the two. Both operations need two vectors for dot product and cross product. Dot produces a scalar, cross produces a vector. All right, when you do that formula that I showed you for cross product, you get three components of a vector, right? It's not a single number. So be aware of that. Now, if they're both perpendicular, we know dot product is 0, which is huge for us. Well, the cross product is actually at a maximum. That makes sense if we think about torque, right? When are we going to get maximum torque? Well, when we're pushing perpendicular on the lever, right? Dot product, one of its big uses, and you're going to see this a lot in some formulas I'm going to show you in 11.6. It projects one vector in the direction of another. We used it last time to find the shortest distance between a point and a line. The cross product, again, its most important feature is that it finds a vector that is normal to the plane that the two given vectors lie in. Now here's something that's interesting. The dot product, we talked about this last time, generalizes into n dimensions. We did it with 2D vectors and 3D vectors. We could do it with 10D vectors, 1000D vectors if we needed to. Cross product, not so much. It's only confined to 3 space only. So if you're working in 2D, you already know cross product is not going to be something you're going to use. Both vectors involve the lengths of 2 input vectors and the angle between them. One of them uses sine, the other one uses cosine. The only time we really need the geometric definition of them is, again, if we have the angle between them, or like you saw in the worksheet last time, if you're trying to find the angle between 2 vectors, you set the 2 definitions of the dot product equal to each other and solve for theta. In theory, you could do that with cross product too, but I highly recommend you don't for 2 reasons. Number one is you got to do the cross product, which is a more complicated mathematical procedure than the dot product. So there's more opportunities for mistakes. Number 2, using inverse cosine is better because the range of inverse cosine is 0 to pi or 0 to 180. With sine, it's negative pi over 2 to pi over 2. And so you won't necessarily, you'll have to deal with negative angles and think about how those work in relation to the angle between the vectors. So always, if you do an angle between 2 vectors, just put the 2 definitions of dot product equal to each other. Stay away from cross. Can absolutely be done, but you're making more work than you need to. Okay.